All right, here we want to look at how we can evaluate some basic limits. And to start off, we want to look at the limit of 5 as x approaches 2. Well, if you notice here, we have a constant function, and if we were to look at this graphically, the limit of 5, well, the graph of 5 would just simply be a horizontal line at y equals 5. And if you think about this, as x approaches 2, well, if we approach 2 from the left side and the right side, what is our y value approaching? Well, if you notice here, our y value is always 5. It's a constant function. So here, your limit then would be equal to 5. So no matter what you have for a limit, if you're taking the limit of a constant function, it doesn't matter what value you're approaching. For example, over here, if we say what's the limit of 8 as x approaches 2, well, once again, 8 is a constant function, so you have a horizontal line, and as we approach 2, your y value, our limit, is approaching 8. Okay, so for this example, what you're looking at is if you're taking the limit where, let's say, of b, where b is any real number as x approaches some real number c, it's always going to be equal to b. Okay, so here b and c are representing real numbers. So the limit of a constant function as x approaches any real number is simply going to be that constant function b. All right, next we want to look at how can we evaluate limits using what we call direct substitution. And in this case, this is what allows us to actually just substitute directly into the function. Now, there's some situations we'll talk about where you have to be careful, but if we have the limit of x squared as x approaches 3, well, we know that x squared, we have your graph here, is a parabola, and we can see that as x approaches 3 from the left and to the right, we're approaching this point right here. Well, and we can tell as x approaches 3 here, we're approaching our y value of 9. Well, with this example, if we have a polynomial, and this is true for any polynomial function, we can simply use this direct substitution, which means we can take the 3 and plug it in for x. So we would have 3 squared, which is equal to 9. So that's your limit. Okay, so again, it's really that easy. As long as you can plug the number into the function and it's defined at that point, most of the time that's going to give you the limit that you're looking for. Again, if we look at this polynomial function here, x squared plus 5. Again, we can take the 3, simply substitute that in for x. So we get 3 squared plus 5, and we get 3 squared is 9, plus 5 is 14. So yes, it really is that easy, okay? All right, let's try this example. Or if you want, you can actually pause the recording and see if you can work this one out on your own. If you notice here, we have x squared plus 2 divided by x plus 1. We want to find the limit as x approaches 2. Well, can we use the direct substitution? Well, if we plug 2 in, we're going to get 2 squared plus 2 divided by 2 plus 1. So we would end up with 4 plus 2 is 6, and 2 plus 1 is 3. So we end up with the limit is 2. All right, now, this direct substitution that we just talked about, that will work for any polynomial function. And the reason it works for any polynomial function is because if you have a polynomial function, you're always going to have a nice smooth curve. Your function is not going to be undefined. And if you notice, we looked at an example here. x squared plus 2 over x plus 1. This is not a polynomial function. It's a rational expression, a rational function, but as long as our point is not undefined, in this case, we could still use direct substitution. Now, if we were looking at the limit as x approaches -1, if this was a -1 here, we couldn't use direct substitution because if we plug a -1 in for x on the bottom, we would get 0 in the denominator. So that's an example where direct substitution would not work. And in that case, we'd have to use another technique or simply look at the graph of the function. Now, here we have the limit of the square root. So if we have the square root, again, it's not a polynomial function, but as long as we can plug this in and it's not undefined, we can still use the direct substitution. So will it work here? Well, we could certainly take the square root of 4, and the square root of 4 does equal 2. So that's your limit. Now again, I know at first this almost seems too easy, but you have to keep in mind that we're really concerned at what's happening as x approaches 4. And in the cases that we're looking at here, we can actually get to 4. Now keep in mind that the limits we looked at before, sometimes we won't always get to that number. We're only concerned about what we're approaching. But in this case, as x approaches 4, our value is approaching 2, and we can simply use this direct substitution. And again, over here, if we have the cube root of x, we want to find the limit as x approaches -8. Can we use direct substitution here? Well, we would take the cube root of a -8, and of course, because it's the cube root, we can take the cube root of a negative, so your answer would be a -2. And even for trig functions, once again, if we want to take the limit of sine of x as x approaches pi, can we use direct substitution? Well, as long as we can take the sine of pi, and can we do that? Well, over here I've drawn the graph of our sine function, and clearly as we approach pi from the left and from the right, we are approaching here, which is 0. Your y value at this point, because we're on the axis, would be 0. And if you take your calculator and you type in the sine of pi, you would find the limit is 0. So once again, we can use direct substitution as long as it's not undefined. All right, let's try one more example. The limit of tangent of x as x approaches pi over 2. Can we use direct substitution here? Well, if we take the tangent of pi over 2, what does that equal? And if you don't remember your tangent is your y over your x, and at pi over 2, if you think of your unit circle, pi over 2, we're at the top of the unit circle, and we're looking at, here you have 0, 1, and remember your tangent is what? Your y over x. Well, if we take our y value divided by x, we're going to take 1 divided by 0, which is undefined. So here, we're not able to use direct substitution because it's undefined. So that means we'd have to use some other technique. Okay? In other words, pi over 2 is not in the domain. Okay, in other words, pi over 2 is not in the domain of your tangent. We can't take the tangent of pi over 2, and over here, if you look at the graph, we can see that if you remember the graph of your tangent function looks like this, and what happens as we approach pi over 2? Well, at pi over 2 we have a vertical asymptote here, and our graph is going to infinity. And if you recall last time, if your function as we approach the value pi over 2 goes to infinity, that tells us then that your limit does not exist. Okay, so to quickly review here, if we go back up, basic limit of a constant function, it's always going to be that constant function. If you have a nice polynomial function, we can use simply direct substitution. And even other functions that we have, such as a rational function or a square root or cube root function, as long as you can substitute in without it being undefined, you can still use direct substitution. And again, even for your trig function, as long as it's within the domain or the function is defined at that point. So again, as a tangent function, we weren't able to take the tangent of pi over 2 with direct substitution because the pi over 2 is not in the domain. And graphically, if we look at the limit, we can tell that it does not exist.